Good afternoon, everyone. Thank you for joining this session. My name is Ozan Tarlan. I'm a PhD student from Ozyegin University, and today I am pleased to present our work titled Qupkiot IoT, Quic-based peer-to-peer public key infrastructure for IoT. This research was conducted by me, Kubra Kalkan Ilgin Safak, and Hasan Sozer. This is a joint effort between Ozan University, University of Jyvaskyla, FIBA R&D Center. Let's begin discussing the outline of this presentation. First, before diving to the technical details, we will begin with the motivation where we explain fundamental challenges in security, IoT communication, and why any approach is necessary. Next, I will summarize our contributions, and following that, we will introduce the key concepts such as decentralized public key infrastructure, peer-to-peer communication, and lightweight cryptography. We will then proceed with the literature review, comparing our work against existing approaches. After that, we will walk through our proposed handshake protocol. Then I will present the simulation results demonstrating the performance advantages of our solution over the existing methods. And finally, we will wrap up with the conclusion and discuss feature work with you all. Okay, let's start with the motivation. In IoT networks are growing rapidly across domains like smart homes, wearables, and industry. And these systems involve millions of low-power devices that need secure, yet lightweight communication. Traditional public key infrastructure is centralized and too heavy for this context. It introduces single points of failure and high overhead. Blockchain-based decentralized public key infrastructures helps decentralized trust, but comes with high storage and computation costs from the encryption, which are impractical for constrained devices. And most current IoT protocols still depend on intermediaries like MQTT brokers, which increase the latency and add different attack surfaces. There is a clear need for a solution that is decentralized, efficient, and tailored to IoT constraints. That's the gap our work aims to fill. Our work introduces three core contributions that address the limitations of existing IoT security frameworks. First, we design decentralized public key infrastructure based on Kademlia Distributed Hash Tables. This replaces traditional certificate authorities with fully distributed trust model, enabling scalable, resilient, and tamper-resistant identity management. It ensures that the authentication does not depend on a central entity, so this eliminates the single points of failure. And secondly, we adapt a Quic protocol for peer-to-peer messaging. Our version, Quic already supports zero round-trip time session resumption, which allows devices to reconnect instantly without repeating the full handshake. Combined with the Quic's inherent support like multiplexing and low latency data transfer, this is well suited for low resource constrained IoT devices. And thirdly, we implement the light cryptographic suite tailored for constrained devices. We use Elliptic Curve Diffie-Hellman and Salsa 20 for energy efficient encryptions. Together, they significantly reduce computational and memory overhead while maintaining strong security guarantees. Okay, let's talk about what is Quic. We will discuss some key concepts of this research. What is Quic? Quic is a modern UDP-based transport protocol originally developed by Google. It combines TLS encryption, congestion control, and stream multiplexing into a single protocol designed for speed and security over unreliable networks. Okay, why use Quic for IoT? It offers advantages like zero round-trip time, which allows devices to resume sessions without repeating a full handshake. And multiplexing, meaning multiple streams can be handled in parallel without head-of-line blocking, something TCP struggles with sometimes. And how we modified it, we tailored Quic to suit peer-to-peer communication among resource constrained IoT devices. Our version eliminates reliance on centralized servers and integrates with a decentralized authentication layer. Combined with lightweight cryptography, this makes Quic practical for high energy efficient secure communication at the edge of the network. So let's talk about distributed public key infrastructure with Kademlia-DHT. To decentralize the authentication, we use Kademlia-DHT as the foundation of the public key infrastructure. Kademlia is a peer-to-peer protocol that allows efficient key value lookups. Each node stores part of the global key value space, enabling a scalable and resilient storage of public keys. This removes the need for a central certificate authority. Devices can look up and verify identities without relying on a trusted third party. Kademlia enables a lightweight distributed public key infrastructure suitable for large-scale IoT deployments. Okay, let's talk about the secure lightweight encryption. IoT devices are resource constraints, so we use lightweight encryption algorithms to minimize the overhead. What are these? These are, for example, for the key exchange, we use Elliptic Curve Diffie-Hellman. It provides strong security with small key sizes and fast computation, which is great for message overheads. And for symmetric encryption, we use SASA 20 FS Stream Cipher with low memory and CPU usage, which is ideal for devices without cryptographic hardware. Together, Elliptic Curve Diffie-Hellman and SASA 20 offer a secure and efficient alternative to heavier protocols like RSA and AES, making cryptography practical for low power IoT environments. Okay, several works, let's talk about the literature review. Several works have explored decentralized public key infrastructures and secure IoT communication, but they come with some trade-offs. Mainly, they focus on blockchain-based decentralized public key infrastructure solutions. This is very common. They offer decentralization, but at the cost of high storage and computation, which is impractical for IoT because like blockchain uses many encryption algorithms and heavy which is also very computation heavy. Other protocols like MQTT over Quic and Co-op over Quic rely on centralized brokers, which introduces latency. So the message needs to be relayed from one point to another, which can create bottlenecks and single points of failure once again. In contrast, our approach uses distributed hash tables instead of blockchain for lightweight scalable key management. It eliminates all central intermediaries and focuses on peer-to-peer quick, tailored for low latency IoT messaging. This combination fills a gap from the current literature to the best of our knowledge. Okay, let's talk about the system overview. Our handshake protocol adapts quick transport layer and integrates it with a decentralized authentication mechanism. We begin with Quic on the transport layer, a protocol that offers fast connection setup and multiplexing and TLS 1.3 integration. It supports zero round-trip time, resumption, and congestion control, which makes it ideal for real-time IoT communications. To remove the central authorities, we use Kademlia-DHT on the application layer. to store the public keys and to authenticate. Devices query this DHT to retrieve the recipient's key during the handshake. This supports decentralized identity verification. For security, we used Elliptic Curve Diffie-Hellman for establishing shared secrets, and SASA20 for encrypting the session data. Our system is peer-to-peer without brokers and enables a secure and low latency communication directly between IoT devices. As you can see from this overview, the attackers can, our attacker model can eavesdrop, replay, and forge messages and can join the network. Let's talk about the handshake protocol. This is the message flow of our authenticated handshake protocol, which enables two IoT devices to establish a secure session without a central authority. First, we use key lookup. The initiating client queries the DHT to retrieve the recipient's public key using their identifier. And then the hello message indicator sends a hello message, including its own public key and 16-byte nonce, encrypted with the recipient's public key. And in the response phase, the recipient replies with its own public key and the XOR of both public keys. And then initializing IV, and then IV encrypted with the sender's public key. This allows both sides to compute the same IV and proceed securely. After that phase, we go to the shared secret agreement. Both clients derive a shared secret using Elliptic Curve Diffie-Hellman and SASA20 cipher with the agreed IV for the encryption. And then we go to the nonce validation. Each device encrypts the received nonce and sends it back. If a device is successfully decrypts its own nonce, it confirms the other party's authenticity. And then we continue with the finished messages. Finally, a symmetrically and encrypted finished message is sent from each parties, confirming that both sides have authenticated each other and share the same session key. And this is basically it for the handshake protocol. Okay, let's talk about the security analysis. Our protocol is designed to withstand attacks under the Dolev-Yao model, where the adversary has full control over the network, which means that it can eavesdrop, replay, or forge messages. Eavesdropping is mitigated through the asymmetric encryption and all the sensitive data during the handshake. And replay attacks fail because each session uses fresh, randomly generated nonces and initialization vectors. And forgery is prevented by verifying that only the trusted nodes can write to the DHT, and all the key entries are digitally signed. To formally validate our design, we also used Avispa span toolset. The analysis confirmed our handshake protocol is once again resistant to common attacks, including like man-in-the-middle attack, impersonation, and key compromise. In short, the protocol guarantees confidentiality and authentication even in adversarial networks conditions. You can check the formal proofs of these Dolev-Yao model in our paper. I will be moving on with our results and discussion section. But before that, we need to talk about some setup parameters. To evaluate our protocol under realistic conditions, we designed an experiment using NS3 simulation, simulating the typical IoT traffic and environments. To get an realistic IoT environment, we used a benign IoT PCAP dataset to extract some critical parameters. To quantify our performance gain, we need to look at the actual real-world data. So To do that, we analyzed some benign PCAP dataset. We looked at the average number of daily connections between devices, which was around 55.6, and the average number of packets per connection, which was around 18. These values were used to generate a realistic message frequency and session counts over a 7-day simulation period, which until then these session tickets expire and you cannot use the zero round trip time. For our network conditions, we adapted various configurations from existing words. For example, for wireless, we used Wi-Fi and 4G and satellite parameters, which the parameters are 12.5 milliseconds delay and 20 megabits per second for Wi-Fi were used. For 4G, we used 50 milliseconds delay and 10 megabit per second internet speed. And for the satellite connections, we used 300 millisecond delay and 1.5 megabit per second speeds. These were the parameters for our NS3 network simulation setup. With these three setups, we cover a wide range of IoT use cases from home devices to even drones. Like these are the setup parameters for our simulation. Now let's discuss the results of our Avispa span results. To validate the security of our handshake protocol, we used the Avispa span formal verification toolset. The protocol was modeled and analyzed against common attack vectors like including replay attacks, man-in-the-middle attacks, and key compromise scenarios. The Avispa span results confirmed that our design satisfies all defined security goals. No vulnerabilities were detected, and providing a strong assurance of the protocol's correctness and resilience under these circumstances. Okay, let's talk about our we discussed the network parameters. Now we will quantify our results in this image. We compared our work against IoT PKI, which is denoted in the green bars. IoT PKI was the closest thing that we have, which used decentralized public key infrastructures using blockchain, and they have a formal, a different formal handshake protocol within their paper. So in our NS3 network simulations, we compared that work with our work. So in this IoT PKI, a decentralized public key infrastructure solution that uses blockchain and TLS 1.2 were used, and we simulated that authenticated handshake protocol in the NS3 simulation environment. So while IoT PKI uses RSA and AES with TCP and TLS, which requires full handshakes and heavyweight cryptography, our protocol uses Quic with zero round trip time resumption, which in TLS 1.2 you cannot do. We also use Elliptic Curve Diffie-Hellman and SASA20 for a lightweight encryption. In networks with repeated daily connections, our use zero round trip time reduced handshake over 25% to 46 handshake overhead, as you can see in this image. And other than this image, Elliptic Curve Diffie-Hellman reduced the public key communication size by 72% compared to the RSA of the compared work. And the SASA20 achieved 42% faster encryption decryption rates, better than the AES in our measured scenarios. which these are calculated using a common computer. Across Wi-Fi, 4G, and satellite links, our protocol consistently outperformed IoT PKI in terms of latency and computational efficiency, that we can say, while maintaining the equivalent security guarantees. This makes it highly suitable for resource-constrained, time-sensitive IoT deployments in our opinion. So let's talk about the conclusion. To summarize, we introduced a decentralized public key infrastructure tailored for IoT, combining Kademlia-based peer-to-peer Quic and lightweight cryptography. Our protocol removes central authorities, minimizes latency with zero round-trip time handshakes, and ensures secure communication for resource-constrained devices. Compared to blockchain-based and TLS-based solutions, our approach achieved lower overhead and better scalability and stronger resistance to single points of failure, all validated through our NS3 simulation. For our future work, we will be integrating a blockchain for authorization and maybe we will add secure DHT entry updates and deletions. And we will be exploring zero-knowledge proofs for privacy preserving authentication. Overall, in other words, our protocol provides a practical, scalable, and secure foundation for IoT communications. Thank you so much for listening. Here's